The purpose of this video is to expand on some of the math and equations that we've been using in the classroom. For the most part, what we've seen so far is the equations have been straightforward. We provide you with an equation, you plug numbers into them, and that gives you the answer in which you're looking for. As we move forward throughout the class, what we're going to start to use and start to understand is how we can use these equations to solve for other parts of the equation. For example, in our equations, we could give you a VO2 and have you solve for a percent grade or a speed or a work rate, etc., etc. And so that's what these questions are really designed to do, is to kind of make you critically think, understand how the equations can be used, and different information can be plugged into them as we go forward. So we'll take a look at our first example here. So this says that a subject is walking on a track at a pace that elicits an oxygen consumption of 12 mils per kg per minute. What speed is the subject walking? So when I see word problems or math problems like this, the first thing that I try to do is look at the question and highlight exactly what is known and what information we can pull out. So the first thing it says a subject is walking. So this tells us that we're going to use the walking equation, that is VO2 equals 0.1 times speed plus 1.8 times speed times grade plus 3.5. So subject is walking. On a track, there's our second one. Our track indicates that the percent grade equals 0% because tracks are flat. I will note, right, in class we showed you the two equations. One was horizontal only, and then this is horizontal and vertical. Note that the equations will give you the same idea because here our percent grade will be 0 and will cause this to cancel out. My personal preference is just to use the entire equation, and then that way we only have to memorize that and don't have to worry about it. The second, or the last part of information that we get from this is that our VO2 is 12 mils per kg per minute. So we're going to be able to put 12 here into our VO2 equation. And the last thing is that we need to solve for speed, which is great. So if we kind of think about, we have our VO2, we have a percent grade, and we have our variable that we're going to solve for, which is speed. So we can do that now. So again, VO2 is 12 mils per kg per minute is equal to 0.1 times our speed plus 1.8 times speed times grade, which is, instead of grade, we should write 0 plus 3.5, or 12 is equal to 0.1 speed plus 0 plus 3.5. And now we solve by subtracting 3.5 from both sides. 8.5 equals 0.1 times speed. Divide both sides by 0.1. Gives us 85 equals speed. So therefore, in our answers, we can say speed equals 85 meters per minute. We can also convert this to miles per hour. To do that, we divide our meters per minute divided by 26.8. Gives us 3.17 miles per hour. So we could also say speed is 3.17 miles per hour. In our next example, we're going to use the equations to now solve for a percent grade and or a speed. Again, this is going to be somewhat realistic as we have a person's fitness level, and then we're going to use this to create an exercise prescription. So let's read the question. A patient asked you to help to determine an exercise prescription. They recently had their VO2 max tested and received a result of 32 mils per kg per minute. So that's their VO2 max, is 32. Since the person has not exercised in a while, their doctor suggests walking at 40% of their VO2 max. Create a treadmill based on these two limitations. Create a treadmill protocol based on these two limitations to exercise. The first thing that we're going to look at here is we need to identify and calculate what 40% of their VO2 max is. So 32 mils per kg per minute times 0.4, or 40% in a decimal, is 12.8 mils per kg per minute. So that's our desired VO2 that we're going to try to create an exercise prescription for. And now, as we move to part A, it says the patient is elderly and cannot walk very fast and wants your recommendation on a speed and a grade. So our goal here is to, of course, pick a speed that is relatively slow. So again, when we're talking exercise prescriptions, again, when we look at our equation of VO2 equals 0.1 times speed plus 1.8 times speed times grade plus 3.5. We're going to be able to pick and choose. So we have two variables, speed and grade, and in this case we're going to pick a speed, solve for grade. In this case we just need something slow, so I'm going to arbitrarily pick 2 miles per hour. That is what I would consider a slow walking speed. So let's kind of get to work then to solve for a percent grade. The first thing that we need to do is convert 2 miles an hour times 26.8 equals 53.6 meters per minute. So there's our speed that we can plug in. We know our VO2, right? We've calculated 12.8 equals 0.1 times our speed of 53.6 plus 1.8 times 53.6 times our grade, which still remains an unknown. Again, you can think about that as x if you would, plus 3.5. And now we would then go about solving this. So this is 5.36 plus 96.48 times the grade plus 3.5. Of course, we need to subtract 3.5 and 5.36. Gives us 3.94 is equal to 96.48 times our grade. Last but not least, we need to divide both sides by 96.48. This gives us 0.041 if we're rounding up. Multiply that by 100 to get it into a percent grade is a 4.1% grade. So therefore our exercise prescription would be 2 miles per hour at a 4.1% grade. The second example of this says a patient feels unstable on high incline ramps and is worried about falling while walking on the treadmill. So in this case, we're going to do the opposite. Instead of choosing a speed, we're going to choose a grade, and we're going to make it a relatively low percent grade. So similar to this, I'm just going to randomly choose one. I'm going to pick a 2% grade as our low incline. Could you pick 0? Sure, but I'm trying to make the math a little bit more difficult and not just plug in 0 to give you guys some examples. So here we go. Our VO2, 12.8 equals 0.1 times our speed plus 1.8 times speed times our grade in a decimal, 0.02 plus 3.5. So we can kind of simplify. 0.1 times speed plus 0.036 times speed. So basically to get that, I just took 1.8 times 0.02 plus 3.5. Subtract 3.5 from both sides. gives us 9.3 equals 0.1 s plus 0.036 s. Now, if we kind of remember, all we have to do is add these together. So this actually becomes 0.136 times speed equals 9.3. Divide both sides by 136. Therefore gives us a speed equals 68.3. So our exercise prescription would be a speed of 68.3 meters per minute. Again, we can divide that by 26.8 or 2.55 miles per hour and a 2% grade. Okay. All right. In our third example, we make the jump from the treadmill now onto the cycle ergometer. Here, again, we're going to have one basic equation that you need to memorize. I will note that, again, in lecture notes, we gave two different equations, one for work rate in kilogram meters per minute and one for work rate in watts. You can go back and forth memorizing both equations, or you can easily convert back and forth between watts and kilogram meters per minute. So here's our question. Calculate the estimated VO2. So we're going to solve for VO2 for a 90 kilogram subject on a cycle ergometer with a power output, or this is also known as work rate, of 115 watts. So let's work on that, and then we'll come back to calculating total energy expenditure. Again, we have two equations. We can look and say that VO2 is equal to 1.8 times our work rate divided by our body weight plus 7. And here, our work rate must be in kilogram meters per minute. Or we could use the second equation, which is simply VO2 is equal to 10.8 times the work rate divided by body weight plus 7, where here work rate is in watts. In this case, of course, we're given watts, so we could solve that one, or the other option is we could convert 115 watts to kilogram meters per minute by multiplying by 6. Which gives us 690 kilogram meters per minute. Since this is an example, I'm going to go ahead and solve both equations and show you that they give you the same answer. So again, we're solving for VO2, and here we have 1.8 times our work rate, which is 690, divided by our body weight in kilograms, which is 90, plus 7. So we simply do the math. 1.8 times 690 is 1242 divided by 90 plus 7. 1242 divided by 90 is 13.8 plus 7, or 20.8. So VO2 equals 20.8 mils per kg per minute. And that would be our answer here. We can come over here and do the same thing. So VO2 equals 10.8 times 115, or our work rate in watts, divided by 90 plus 7. 10.8 times 115 gives you 1242 divided by 90 plus 7. 1242 divided by 90 is 13.8 plus 7. VO2 equals 20.8 mils per kg per minute. So again, it doesn't matter. It's up to you. You can memorize one equation or the other, just making sure that you can easily convert between watts and kilogram meters per minute using that conversion factor of 6. The second question, the second part of this question says calculate the total caloric expenditure for this exercise. I will note, and I'll update this on here, I didn't actually specify a time in this example. So before we do, let's say we're going to do this for 30 minutes is how long I plan to do the exercise for. So here's our caloric expenditure. So since we're calculating total, we need to calculate the number of liters of oxygen consumed over the entire exercise period. So our VO2 equals 20.8 mils per kg per minute. And we need to get this into total liters so that we can then convert total liters into kcals. To do that, of course, we need to multiply by all the stuff to get rid of it. So we're going to multiply by 30 minutes to cross out minutes. We're also going to multiply by our body weight, which is 90 kilograms. Tells us that we get 56,160 milliliters of oxygen. So 56,160 then divided by 1,000 gives us 56 liters of oxygen. And then we know that we burn 5 kcals per 1 liter of oxygen. So 56.160 times 5 gives us 255.8 kcals. Sorry, just kidding. I just realized that I did something in the calculator wrong. 56.160 times 5 equals not 255, equals 280.8 kcals. So a little bit of math was done wrong in the calculator, but that's the correct answer there, 280. Our next question is a question that I've used in the lab, but I think it's such a great question that and gives us a lot of practice, so I've used it again here. So this is talking about the concept of trying to run a 2-hour marathon. So to accomplish Nike's push to break a 2-hour marathon, a runner would have to run at 13.1 miles per hour for the entire race. Hence, right, a marathon is 26.2 miles. So marathon is 26.2 miles. Calculate the equivalent resistance and RPM on the cycle ergometer to 13.1 miles per hour, assuming a 1% grade for the marathon. So that's going to be the first part of the question, is to calculate that. Then we're going to do how many calories did they burn during the entire marathon. So let's kind of think about what we know here. So the biggest question that we kind of have to think about is we have all our values in the running category, right? 13.1 means that this is going to use the running equation. And somehow we need to connect that to the equation seen in the cycle ergometer. So again, I like to start out by just writing out our equations that we know we're going to need to use. So VO2 for the running is 0.2 times speed plus 0.9 times speed times grade plus 3.5. Conversely, our cycling equation is VO2 equals 1.8 times work rate divided by body weight plus 7. So if we look at these two equations, what we could try to do is we could try to figure out speed and grade and calculate it into wattage. But at least in our class, we haven't discussed how to do that. Or we could say the other two things that are similar between these two equations here are VO2. So basically what my plan is to solve this is to use our numbers in here. We have a speed and a grade, so speed and a grade. We'll plug it into our equation, we'll get VO2. Then we'll use that VO2 to then solve this equation for work rate. And then we'll convert work rate then into RPM and resistance. So let's do that as we go. So first let's solve VO2 while running equals, let's see here, first 13.1. So 13.1 times 26.8 equals 351 meters per minute. So our VO2 equals 0.2 times 351 plus 0.9 times 351 times 0.01, or 1% grade in the decimal, plus 3.5 equals 70.2 plus 3.159 plus 3.5 gives us a VO2 76.9 mils per kg per minute. So it's estimated that during this race he has a VO2 of just shy of 77, which is pretty amazing. Now we need to, of course, calculate this into our cycling equation to solve for work rate. So here we're going to solve for work rate. So our VO2, 76.9, is equal to 1.8 times our work rate by our body weight, which we have in the question, which is 55.9, plus 7. I'll note up here I drew parentheses just to make sure that we do that. Please excuse my dearness. Sally says we do all of this before we add 7. Anyway, so it's the same thing. Sorry for the confusion of the notation here. So to solve for this, so first we're going to kind of work our way backwards. We're going to subtract 7. And then we're going to multiply by 55.9. We're going to divide by 1.8. So in this case, 3907 divided by 1.8 gives us 2170, and this is in kilogram meters per minute. So here's our work rate. The next thing that we need to, of course, do is calculate this into a resistance and RPM. So in this case, we can use the power, or work rate, is equal to resistance times RPM times 6. That's how we quickly calculate power on the cycle ergometer. Again, two variables, so we're going to use one and solve for the other. In this case, I'm going to pick a resistance and solve for RPM. So 2170 equals, let's say, 5 kilograms of resistance times our RPMs times our 6. 5 times 6 is 30 times RPM, 2170. Divided by 30 on both sides gives us an RPM of 72.33 revolutions per minute. So again, to answer the equation and to solve for, so an equivalent exercise on the bike would be a resistance of 5 kilograms and an RPM of 72.3. Next, we want to say, based on the liters of oxygen consumed, how many calories did he burn during his 2-hour and 25-second race? Here we're going to we'll start a new page. Again, his VO2, 76.9 mils per kg per minute. We know his body weight from the question is 55.9 kilograms. And the time that he spent exercising, I'm going to convert, is 2 hours and 25 seconds. So we need to convert that into minutes. So similar to other questions that we've done before is solving for total kcal. First, we need to get this into minutes. So 2 hours is, of course, 120 minutes. 25 seconds is 25 divided by 60 is 0.41 minutes. So 120.41 minutes for the entire race. So now we can plug that in, 76.9 mils per kg per minute times 55.9 kilograms, we'll cancel that out, times 120.41 minutes, we'll cancel that out. 607. Rewrite that again. So that gives us 517,607 milliliters of oxygen. Now we need to divide that by 1,000 to get it in liters. Gives us 517.6 liters of oxygen. So that's his total liters of oxygen, 517.6 times 5 kcal per liter. Tells us that he burned approximately 2588 kcal. So 2,588 kcal was his estimated calorie expenditure during the race. Our next question is also from a lab example, this one on the cycle ergometer with multiple steps. So in this case, our Tour de France winner, Chris Froome, averaged a power output of 2,340 kilogram meters per minute during the last 15.3 kilometers of a mountain climb in stage 10 of the 2017 Tour, of which, I'll note, he won the entire Tour. It took him 41 minutes. He weighs approximately 67.5 kilograms. Calculate his relative oxygen consumption. Again, this is straightforward. This is just VO2 equals 1.8 times work rate divided by body weight plus 7. So we have his work rate, we have his body weight, so we'll just plug them in and go. So 1.8 times 2340 divided by his body weight of 67.5 kilograms plus 7. I'm going to do the quick math since this is so straightforward. So 1.8 times 2340 gives us 4212 divided by 67.5 gives us 62.4 plus 7 gives us a VO2 of 69.4 mils per kg per minute. Calculate the total number of kcals burned during this part of the race. Similar to our previous example, we're going to walk through this assuming that this was his average VO2. We have our time, we have our body weight, and so we can calculate that out. So again, 69.4 mils kg per minute times 67.5 kilograms times 41 minutes. Those will cancel out. Gives us 192,064.5 milliliters of oxygen. We'll divide that by 1,000. All right, so we'll convert this into liters. We'll divide by 1,000, so 192,064.5 divided by 1,000 basically tells us that he consumed 192 liters of oxygen. We take 192 liters times 5 kcals per liter of oxygen equals 960 kcals. Last but not least, calculate a speed and grade on the treadmill that would equate this power output. Hint uses estimated VO2. So again, just as our previous example with Kipchoge in the running, the thing that can link VO2 and the the bike and the treadmill is VO2. So we know his oxygen consumption is going to be 69.4 mils per kg per minute. Obviously, this is a high VO2, so we're going to need to use the running equation. So 0.2 times speed plus 0.9 times speed times grade plus 3.5. Again, we now kind of come to the scenario in which we have two variables and we're trying to give an estimated prescription. So we're just going to pick one and solve for the other. I'm going to pick a speed, so I'm going to say 8 miles per hour, and then solve for the percent grade. So first, 8 miles an hour times 26.8 converts to 214.4 meters per minute. We can plug in and get our value. So 69.4 equals 0.2 times 214.4 plus 0.9 times 214.4 times grade plus 3.5. This is 1072. This is 192.96 times grade plus 3.5. So 69.4 sorry, that obviously makes no sense. 42.84. So subtract 3.5, subtract 42.84. Is 23.09 is equal to 192.96 times our grade. We need to divide that by 192.96. So our grade equals 0.1196, and we'll convert that to 11.96%. So again, our exercise prescription, or this would be a speed of 8 miles per hour with a percent grade of 11.96. Our next question, I think, is a relatively good example of another applied question. In this case, I'll read the question and say, a client comes to you and asks you to help them get ready for a marathon. Their goal is to run the marathon, which is 26.2 miles, in 3 hours and 30 minutes. Basically, we need to get to their training and understand what they need to do. So the first thing that we need to do is say, what speed will the runner have to run to maintain this time? So to do that, we're going to take the distance divided by the time that they want to run it in order to convert to miles per hour. So 26.2 miles divided by 3 hours and 30 minutes, which is half an hour, gives us 7.49 miles per hour is needed to meet this time. So if they run 7.49 miles per hour, they'll complete a 3.5 hour marathon. Let's quickly, we know we're going to need this in meters per minute, so let me convert that into meters per minute. So 7.49 times 26.8 tells us that this person is going to need to run 200.7 meters per minute. So next, what we need to do is start to work on their VO2. So let's read the next question. It says, assume their lactate threshold occurs at 70% of their VO2 max and OBLA at 80% of their VO2 max. What will their VO2 max need to be in order to meet their time goal for this race? So first, let's start with this concept. What is our VO2 going to be when we're running at this speed? In this situation, I'm going to assume a 1% grade for the marathon. If you're curious, you can look up marathon courses, so if this was a real scenario, and they'll actually tell you what the percent grade over the average over the entire course actually is. So you could plug that in. I'm going to use a 1% grade because that's a classic way that we equate running on the ground to running on a treadmill. So let's calculate the VO2 that we need to do that. So VO2 is simply 0.1 times our speed. I'm going to go ahead and do it in here since we've done it enough. 0.7 plus, sorry, I need to take that back. We are doing running, so this is the running equation. 0.2 times speed plus 0.9 times speed times grade plus 3.5. So this will give us our VO2 when we calculate it. So we add those all together. So our data tells us that to run 200.7 meters per minute at a 1% grade, your estimated VO2 would be 45.45 mils per kg per minute during the race. So I like to add this as during the race. But the question says, what should their VO2 max be? Obviously, their max has to be higher than what the race is because we can't run the race at our VO2 max. And indeed, we can run it at a given pace. We go back to our question. It says the lactate threshold occurs at 70% of their VO2 max and OBLA occurs at 80%. There's a little bit of misinformation and a little bit of push to remind you back from exercise phys that we know that OBLA, as long as you stay below OBLA, that is where fatigue will occur. So we can ignore lactate threshold at 70% as long as we remain under our OBLA, which here we're going to estimate is 80% of their VO2 max. So basically what we need to say is 80% of their VO2 max needs to equal this number here. So sometimes I like to just give an example to make sure that we go back. So if we kind of think about earlier, we solved 40% of VO2 max. We said VO2 max, so we're going to say this is an example. VO2 max times a decimal equals 40%. So times our percent as a decimal. Again, 40% equals 0.4 as a decimal. So all we would take is, in that case from our earlier example, 32 mils per kg was our max, times 0.4 equals 12.8 mils per kg. So based on that example, all we need to do is plug in the reverse. So we know our decimal, we know our answer, now we just need to solve for VO2 max. So let's do it with our answer here. So our VO2 max is, we'll call it, we'll say VO2 max times our percent as a decimal. Again, we're aiming for 80% of our VO2 max. And then we know that our answer that we get when we multiply this is 45.45. So now to solve this, we just divide both sides by 0.8. And this would tell us then that our VO2 max needs to be 56.81 mils per kg per minute. So therefore, if a person wants to exercise at 80% of their VO2 max, they need to have and where 80% is equal to 45.45, then they need a VO2 max of 56.8 mils per kg per minute in order to run and complete that marathon at 200.7 meters per minute.